So welcome back. We're going to talk about principles of SHM, and we're going to start with drawing a graph. So what I'd like you to do is to draw yourself some axes with time along the x-axis and velocity along the y-axis, and I'd like you to consider looking especially at this spring here, what happens, or a sketch of the velocity change with time. And in order to help you, I would suggest you have another graph above, which is displacement time. So just like we started last time, try and draw yourself a displacement time graph, and you can again use this spring to help you with that idea of what you're looking for. And then underneath, draw yourself a velocity time graph that matches those same times. So well done for having a go at that. So let's think about what's going on. So here is our spring. At the two turning points, we see the spring's velocity has gone to 0. So right up here, the 0, and right down here, the 0. So at the maximum amplitude, our velocity is 0. So when the displacement is maximum, the velocity is 0. When the displacement is 0, so when it's at the central point, the velocity must be maximum, because right at the centre it's travelling at its fastest speed going through. And then when the displacement is negative maximum, so we were talking about the opposite side, the velocity must also be 0. So if we go to the visualizer and the PowerPoint, you can see I've set up some graphs here, and I've put along the x-axis we've got time. On the y-axis, we're going to have two different values. We will have displacement and we will have velocity. I'm going to do them in two different colours so we can see the difference. So I've also drawn my 6 stages, or 6 of my stages, to give you an idea of what is happening as we talk through it. So here I'm going to start my spring at the biggest negative displacement. So this is where I pulled the spring down and we are starting to curve. So we'll put a little cross there. So when it goes through 0, it's going to be that time there, and then it goes to the biggest positive displacement, so that's going to be that time there. And I'm sure you can now see what we're going to have is our inverse cosine. So it'll look something like this, which I'll now draw on. So it's going to curve around like that, curve back and back down, curve back round, back up, and something very similar to that. Okay, so there we got our displacement time curve, and we're seeing that the displacement starts in a negative direction, so this is my negative amplitude because maximum displacement, and then it's going to go to my positive amplitude, which is my positive displacement maximum, and it's going to go through 0 at those times there. Now if we look at the velocity, let's think about what's going on at these stages. So in this first stage, my velocity when I'm at negative displacement, because it's turning around, is in fact going to be 0. So at this point my velocity is changing direction, sorry, my spring is changing direction, and in order to do that, my velocity must have gone to 0. As it's travelling through the centre, at this point here, because it's on the equilibrium line, I've actually got balanced forces, which means I've got no acceleration or deceleration, so my velocity must be its maximum. And then when I go above my equilibrium line, so I've squashed my spring, I've now got a force. Let's draw some forces on here. So I've got restoring force from the spring pulling upwards. I've got no forces acting on this because it's equilibrium. Then I've got a force of the spring pushing downwards. So I must have another 0 velocity. If we go back through equilibrium here, I've got 0 forces or no resultant force, so therefore my velocity must be maximum again. And then we go to our maximum negative amplitude again. We're going to see there's a restoring force towards the centre, and so we're going to have a Vmax again. And finally, when we reach, sorry, we're not going to have Vmax, we're going to have V0. And then finally, when we reach equilibrium, as we're coming back through equilibrium, we're going to have no forces on it again. So we're going to have AV max. Now we also need to think about the directions of these velocities. If this, so let's go for green. Let's put velocity arrows on the maximum ones. Well, this one is going upwards. So we can say that that's going to be in a positive direction. Yeah, because we've called a downwards a negative direction, so that's going to be a positive direction. Here, we're going downwards, so that's going to be a negative direction. And finally, we're going back upwards, so we've done a whole cycle. We've gone from there to there, and then back round again. So let's draw this on, and we'll draw it in red. So when we're at negative displacement, negative amplitude, our velocity is going to be 0. Because at that point we are turning around, so therefore there's a resultant force acting upwards, which means we've got an acceleration in the opposite direction, so we're going to have a 0 velocity at the turning point. So we're then going to come through 0. So we're going from negative to positive, so that's going from this way. So we're going to have a maximum velocity. So we'll go up here for a maximum velocity. We're then going to reach the top displacement, so we're in the positive amplitude here, and we're going to go back to 0. And here we're coming back through our equilibrium point, so again we're going downwards this time, so it's going to be negative, so we're going to have a negative velocity this time, so turning point. And we'll reach our lowest point, our negative amplitude, and we're going to have a restoring force back to the centre from the spring, which is going to give us a 0 velocity again. And I'm sure you can see we're going to end up with exactly the same graph, but it has just been, it's just out of phase. So we'll just draw this on. So there is our velocity graph. And hopefully you managed to draw that whilst you were from the information that we had. Okay, so we've managed to do displacement, we've managed to do velocity time. Let's do an acceleration one. Let's see if I can draw this a bit freehand. It's not going to be quite so good as the other ones. But we're splitting it into effectively quarters of a cycle, so quarters of a frequency, which is just allowing us to see what's happening at each stage. And we'll look at this a little bit more depth in a moment, because we've got a nice animation to use to get there. So if we think about, we need to think about forces here really. If we think about this first stage, and we can see that we have a restoring force acting upwards, so in a positive direction, even though our displacement is negative, our acceleration at this stage, we'll use green for acceleration, so our acceleration at this stage is going to be positive maximum. When it goes through the equilibrium line, there's no restoring force, there's no overall force, so no net force in either direction, so therefore we know from Newton's second law that the acceleration must be 0. And once we reach our maximum displacement, we're going to have an acceleration back towards the centre, so this time we're going to have a negative maximum acceleration. Moving on to this one, we're back at the equilibrium point, so hopefully you've now realised that the acceleration will be 0 again. So we're not accelerating either way, we're at maximum speed, so we've got no acceleration. And when we reach our maximum negative displacement, then we're going to have an acceleration back in the positive direction. And finally, once we reach equilibrium, we'll be back to 0. So let's draw this on our curve. So we're at negative displacement to start off with, so our acceleration is going to be at maximum value. We're then going to go through 0, and we're going to go to our maximum negative direction, back to 0, back up to positive, back to 0, back down to negative, back to 0, back up to the positive, and hopefully you can see, again, we've got a nice, let's see if I can remember how to draw this nicely. upside down, we've got a nice sine curve, cosine curve, sorry, this time. So we had an inverse cosine for our displacement. And again, this all depends upon where you take your first step for your measurement, because obviously if you take your first step here, so if you started it at the equilibrium point but it still had a mass on and it was kind of going upwards, then this would be your graph. And if you took it from the maximum negative amplitude, so in other words you've squashed it up, then you would have this as your starting point, but everything would just be shifted by a quarter of that wave. So we've got our positive maximum acceleration and our negative maximum acceleration, and in the same way we've got our positive maximum velocity and our negative maximum velocity. So 3 really, really important graphs that you're expected to know and be able to use in any exam. Okay, so we're going to have a look at a simulation now to actually give us an idea as to how this all works. So this is a PhET simulation, and you can access this as well, and I'll put the link in the description so you can see it. And we're going to work with the vectors one today. Next lesson or lesson after, we're going to look at the energy one, but today let's look at the vectors one. So this gives us an idea of what's going on. Let's turn vectors off for a moment, and actually let's reset it. So we've got 2 springs. We can take our mass and we're going to hang it to the bottom of the spring, and we're going to allow that spring to oscillate, and it's oscillating in simple harmonic motion. And we'll come to the definition of what really simple harmonic motion is sort of later on in these lessons, but today just know that that is following simple harmonic motion. Now let's put our displacement and our natural length. So where the spring would sit is our natural length, and this is our displacement. Now, it's unfortunately not going from the equilibrium line. We have to put the equilibrium line in to see that, and we can see that it's moving between the 2. In fact, actually, I want to stretch it just that little bit further. Hang on a second. Let's go beyond the mass equilibrium point. Okay, and we're going to just slow it down so we can start to see what's going on. And in fact, I'm going to get rid of the displacement so we can just see it oscillating around this mass equilibrium point. So let's look at velocity, because what we've talked about so far, and looking back at the graph, is that the velocity, when it passes through the equilibrium point, is at its maximum. And we can see this here from the size of the vector arrow. So that green arrow is showing us the velocity as it passes through that equilibrium point. You can see that green arrow is at its maximum, and then it starts to decrease, and that's because of the forces of the spring pulling it back basically, or pushing it outwards because it's being compressed. Now let's link this to acceleration as well. So the yellow arrow now shows us the acceleration, and what you should hopefully notice is that yellow arrow is always acting in the opposite direction to the displacement. So as the displacement is acting in a negative direction, my acceleration is in the positive direction, and the same in the opposite way round. So if it's in the positive direction, my acceleration is in the negative direction, and that's because of the net force. And again, look very closely at the net force arrow here. As it passes through that equilibrium point, the net force goes to 0 because the weight is then balanced with the force due to the spring. And so you can see that the acceleration is linked with the force. So if you know the acceleration, you could work out which direction the force is in. But it's always in the opposite direction to the direction of the displacement. Okay, so acceleration is the negative, it's a constant multiplied by the negative displacement. Okay, this is something that I would recommend you have a play around with in your own time, because you can learn quite a lot from it, and certainly we'll be using the energy and the labs in the later sessions that we do. So going back to what we talked about, you'll see that these are the opposite to what we've drawn so far, but that is just because they have started at different points. So we have started with a negative displacement, whereas this graph has started with a positive displacement, but everything else fits perfectly to what we're expecting to happen. And we've divided it into the pi by 2, the pi, the 3 pi by 2, and the 2 pi, because this now gives us an idea of how much of a cycle we are out by. So again, displacement, velocity, acceleration. Very, very similar, in fact, exactly the same as what we've drawn, except that we've moved our start point by a little bit. Okay, so we're going to talk about some of the theory that goes with this, and these are quite important comments to understand. So we know from our statics that we did right in year 1, we know that velocity is the gradient of a displacement time graph. So the change in displacement over the change in time gives us the velocity. Now, I pointed out 2 points here. We can see the maximum velocity where we've got the greatest gradient is where we're passing through the zero displacement. So we've got a nice straight line here, and that's got the greatest gradient at that point, so it's the maximum velocity. And also at a turning point, so the point where we turn around, we must have zero velocity because the gradient becomes zero at this point here. So if you take your tangent to the curve at that point at the bottom, you'll find that you've got a zero gradient, so therefore your velocity must be zero. Now we can do the same for the velocity time curve, because again, from the statics lessons, the kinematics lessons, we know that acceleration is the gradient of a velocity time graph. So again, looking at the point where the velocity is zero, we can see we've got the maximum acceleration because we've got the greatest gradient. And remember that this is all now tied back into the forces that are taking place as well. And we've got zero acceleration at the turning point, so when the displacement is zero, the acceleration is zero, because this is where your velocity is changing direction. So as it passes through that equilibrium point, the velocity changes direction, and always changes direction in the opposite direction to the displacement. So that's the acceleration curve. So each one is what we would call a differential of the previous one. Okay, so the differential of the displacement gives us the velocity, and the differential of the velocity with respect to time gives us the acceleration. And the way you need to think about it is this idea of gradient. So the gradient at any point on the displacement time graph will give you the velocity, and the gradient at any point in the velocity time graph will give you the acceleration. Okay. Hopefully that makes a bit of sense, I'm hoping. Now, what we do need to know is the acceleration is always in the opposite direction to the displacement. And I don't know why we've got velocity curve on here, but if we go back and look at the displacement curve, you can see that they're exactly the opposite. So if the acceleration is negative, the displacement is positive. If the displacement is negative, the acceleration is positive. So there's a relationship between those two parts. And this is sort of the last bit of this lesson. We've just got to understand our first equation of simple harmonic motion, which is this idea of acceleration. So acceleration is proportional to the displacement, which we can agree with because we look back at that graph, we can see that they are definitely proportional. When one changes, the other changes. So there's definitely a proportionality there. And acceleration is always in the opposite direction to the displacement. So acceleration is proportional to the negative displacement. And we know when we have a proportionality symbol here, we can actually add a constant of proportionality, which we can call c. So acceleration is then equal to minus c times x. Now, important things that we need to understand here is the shorter the time period, the faster those oscillations are. So the constant is going to be greater the shorter the time period. And we'll come back to that in topic 18.3. So next lesson, we'll explain a bit more why this c value is omega squared. But for the moment, just accept that it is. And omega squared obviously is our angular frequency. Okay, so 2 pi divided by the time period. So here we've now got our first SHM equation, which is going to be acceleration equals minus omega squared x, where omega is 4 pi over t, and t is the time period. Okay, so this is the end of the Principles of SHM lesson. Hopefully that's all made sense for you.